Now we move on to our step number 3. In this step, we're going to show the optimality of the bound square root of n over k. Specifically, we're going to show that this number, as the radius of the largest ball in this cube, can be actually attained. To this end, the first thing we're going to do is that we're going to study this matrix M and find more properties of it. Firstly, we observe that from the fact that M is a similitude and it dilates a vector by a scale of R, we know that M must preserve the inner product. So you can replace one of those X by Y. Here the vectors are from Rk. M is from Rk to Rn. In case you don't know how this follows from here, let me remind you an identity of inner products. So once you know this identity is true for any single vector x, you can use this identity to show immediately that we have that M preserves the inner product up to a scale of R squared. And it follows from this identity. So if you write the inner product in the matrix product form, from here, we must have MTM equal to R squared times IK. If you choose X and Y be any pairs of canonical basis elements in Rk, you get this. Okay, so we have learned more information about this matrix M. And now we go back to look at the inequality we derived from here. We observe that the only place where we have inequality, kr squared less than or equal to n, is here. So the question when this inequality becomes an equality is the same as the question that when this inequality becomes an equality. Because this inequality comes from the fact that each v sub I has its 2 norm less than or equal to 1, which comes from, remember, each v sub I is a column of the matrix MT, the transpose of M. So the question becomes, can we find the matrix M such that its transpose, the columns of this transpose into vectors v1 through vn, can we have those vectors be of norm 1? So let me write down what I said. First, let me mark this inequality with an asterisk. So R squared times K is equal to N, or R is equal to N divided K square root, if and only if the 2 norms of VIs are all equal to 1. But we can also rewrite this using matrix M. What does this mean in terms of the matrix M? You know that since MMT, because MT is this matrix, and M itself is its transpose, so we observe that on the diagonal, we get the squares of the norms of V sub n. So this is also equivalent to that the diagonal of MMT are all ones. And now if you combine this condition and this condition, notice that this equation is already implicit in here. When we talk about this R, we always mean this R refers to this scale of dilation. Now, if you look at both of them, you'll realize that we have transformed our question into a purely linear algebra problem. This problem is, for k less than or equal to n, can we find an n by k matrix M over real numbers such that first MTM is n over k times ik. And second, the diagonal entries of MMT are all ones. So this is the question. And now I'm going to show you there does exist such an M. Indeed, we let L be this matrix, square root of n over k times ik 0, this block matrix. This is an n by k matrix. Then, if you look at its transpose, L transpose will be a k by n matrix. And if you look at LT times L, this product will be precisely n over k times ik, which satisfies our first requirement. But unfortunately, if you look at LT, the product in the other way, this guy is equal to n over k times this matrix. This is an n by n matrix whose left top corner is the identity matrix ik. This product does not satisfy this requirement. It's not just because it has a scalar n over k in the front, but also because there are zeros on the other n minus k entries on its diagonal. But the good thing is, if you look at the trace of this matrix, the trace will be equal to n divided by k times k, which is it. Now, is it possible that we transform this product into some matrix whose diagonals are all ones based on this information, that the trace is equal to n, which is n times 1? The answer is yes, we can do this. This is because if we instead look at the trace of LT minus IN, then we get this equal to n minus n, which is 0. To this end, we're going to use a lemma from linear algebra. The lemma states that if A is an n by n real matrix with trace equal to 0, then A is R orthogonally similar to a matrix with 0 diagonal entries. We'll prove this lemma in the next video. But first, it's not hard for us to see that we can use this lemma to finish our solution to this problem. By this lemma, there exists O and n by n orthogonal matrix such that O times LLT minus In OT diagonal entries are all 0. And it follows from here and the fact that OT is the identity matrix. We have OLLT, OT, diagonal entries are all ones. Now we take M to be the product of O and L. Then MMT, diagonal entries are ones, and MTM will be equal to just LTL, which is n over k times ik. This is what we just computed. So we have found a matrix satisfying those two equations, which, by our discussion here, finishes our step number 3.